Hey there, algebros and broettes. We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Welcome. Today we're going to talk about vector spaces and subspaces. We're going to be sort of revisiting some topics, but going a bit further with them and discussing them a bit more in depth. First, let's talk about what it means to be a vector space. We've talked a bit about these, but we haven't seen the definition yet. A vector space is a non-empty set, capital V, of objects, called vectors, on which are defined two operations, called addition and multiplication by scalars. Scalars referring to real numbers. And these are subject to the 10 axioms or rules listed below. These 10 axioms must hold for all vectors u, v, and w, and for all scalars c and d. So we have vectors u, v, and w in the vector space V, and then all scalars referring to real numbers c and d. Okay. And Lily's here to help us with those 10 axioms. Let's talk about it. First of all, we need the sum of vectors u and v, denoted by u plus v, is in the vector space capital V. Second, how I add the vectors doesn't matter, right? We have this nice commutative property that u plus v is the same as v plus u. So if I add vector u and then vector v, it's the same as taking vector v and adding vector u to that. We have a nice associativity property third that says if I add vectors u and v together first and then add vector w, that would be the same as adding vectors v and w together first and then adding vector u to that. So a nice associativity property. Fourth, there is a zero vector, and that's the zero vector in vector space V, such that vector u plus the zero vector is equal to vector u, so we have an additive identity. For each vector u in vector space capital V, there is a vector minus u in vector space V, such that u plus minus u gives us the zero vector, so we need an additive inverse. The scalar multiple of vector u by scalar c, denoted by c times vector u, is in vector space V. And then now we get some distributive properties, right? So scalar c multiplied into, and here we have the collection vector u plus v. I have a left distributive law that says this is the same as c times vector u plus c times vector v. If I have a collection of scalars, so that's c plus d in parentheses times vector u, I have a right distributive law that's c times vector u plus d times vector u. And then I can collect scalars a bit differently. So here I have c times and then the collection d times vector u. I could group c times d and then multiply that as the scalar into vector u. And the last, the 10th property, is a multiplicative identity that 1 times the vector u must give us vector u back. So we need that multiplicative identity. Okay, so going back over through these properties, you'll notice that a few of them are actually familiar to us. And the ones that are, I don't want to say that some of these properties are more important than others, but of this list of 10 axioms, the ones that really stick out are 1, 4, and 6. That's not to say that we don't need the others, but in fact, these three are familiar to us, that we need to be closed under addition, that I need to contain the zero vector, and I need to be closed under scalar multiplication. So these are ones that we're familiar with. The rest of these talk about some other properties, right? Commutativity, associativity of adding in the vectors. I need this additive inverse. I need a left and a right distributive law. I need to be able to collect scalars, and I need a multiplicative identity. Those, those are important as well. But really, these three properties that we talk about of these 10 vector space axioms are ones that we've dealt with before. So we're going to actually talk about them a bit more today as well. There are a few other things to clarify here. For each vector u in vector space capital V and scalar c, we need the following. 0, the number 0, times vector u is equal to the zero vector. Any scalar c times the 0 vector is going to give us the 0 vector. And when we talk about this vector negative u, we talked about that in our additive inverse property, that this is the same as negative 1 times vector u. So these are 3 other things we want to consider. But going back to those 3 vector space axioms, 1, 4, and 6, that we say, hey, we've seen those before, what do we remember them from? We remember them from subspaces. We would say, well, if I want to show that something is a subspace of a vector space capital V, this would be a subset H of vector space V that has the following 3 properties. I need that 0 vector in that subset H. I need to be closed under vector addition. So that means if u and v exist in H, the sum u plus v is in H. And I also need to be closed under multiplication by scalars. So that means if I have an element u that's in the subset H, and any scalar c, any real number c, I need that c times vector u stays in H. We've dealt with this before, so we're really going to be talking a lot about subspaces again when dealing with vector spaces. And we have a very nice theorem that connects these ideas together. This is a very important theorem for the course. We would say if we have vectors v sub 1, v sub 2, so on and so forth to v sub p, are vectors that live in a vector space capital V, then the span of those vectors is a subspace of vector space V. And that's going to be very important for what we're going to be talking about here today. Now, before we start talking about vector spaces in general, let me just give you some ideas of vector spaces that we've already talked about. And some of the best examples of vector spaces are talking about different spaces dealing with real numbers. So an example of a vector space could just be R, our real number line. Or if I want to talk about our Cartesian plane, R2, it's another example of a vector space. If I want to work in 3 dimensions, R3 is a vector space, and so on and so forth, right? It doesn't have to stop here. You say, well, R squared, R cubed, R2, R3, right, for example, are all vector spaces. But I can continue on. And really, when we talk about vectors and the size of those vectors, we can talk about the vector space that they belong to, is really the idea. But that's not the only possibility. We can also talk about a polynomial space as a vector space. So here we have a definition of this. For n greater than or equal to 0, the set P sub n, so this would be sort of bold. It's very similar to vector space Rn. In general, we say vector space Rn, where we have R, and then we have a superscript n. For polynomial spaces, we use P instead of R, and then we have a subscript n. But the set Pn of polynomials of degree at most n consist of all polynomials of the form polynomial P at t equals a sub 0 plus a sub 1 times t plus a sub 2 times t squared plus a sub 3 times t cubed plus so on and so forth plus a sub n times t to the power of n. So here we're talking about polynomials of degree at most n. And there's something important to sort of mention here about how polynomial spaces relate to sort of more traditional vector spaces like Rn, for example. But before talking about that, let's just sort of go through some ideas here. So I'm not going to go through all 10 axioms to show that a polynomial space is in fact a vector space. You could certainly do that, but let's take a look at least those 3 important properties that we're sort of showcasing that we've already dealt with subspaces. So if I go ahead and pick on, let's say, a polynomial P at t, which here I'm going to go ahead and say, well, this is just, we have real numbers, a sub 0, a sub 1, a sub 2, so on and so forth to a sub n. I mean, in this case, let me just call it, for example, I'll do b sub 0, b sub 1t, b sub 2 t squared, b sub 3 t cubed, plus so on and so forth, till we get to the end, b sub n t to the power of n. And if I take another polynomial, q at t, and say this is of the same form, so some constant c sub 0 plus c sub 1 times t plus c sub 2 times t squared plus c sub 3 times t cubed plus so on and so forth, plus c sub n times t to the power of n. These are both examples of polynomials that meet this description, where all the b values and all the c values are just real numbers. These are both polynomials of degree at most n. If I were to add these together, so what if I were to take these 2 elements that exist in the polynomial space and add them together? What is that going to give me? Well, that's going to give me some new polynomial, namely p at t plus q at t. What's going to happen here is I'm going to add and sort of collect like terms, and I'll skip over some of the steps there, but I'm going to have this constant term b sub 0 plus c sub 0, and I'm going to have a coefficient on t when I add these together. That's going to be b sub 1 plus c sub 1 times t. I'm going to have a coefficient on t squared, b sub 2 plus c sub 2 times t squared. And just so I don't run out of room, I'll do plus dot dot dot. And then, same thing with adding the t cubed terms. I can collect the coefficient b sub 3 plus c sub 3. And then at the end here, my coefficient on t to the power of n, well, that's going to be b sub n plus c sub n, and then quantity times t to the power of n. And adding these real numbers together for my coefficients and my constant term just give me some other real number. So we could rename it if I'd like to. I could say, well, this is some constant to a sub 0 plus some constant to a sub 1 times t plus some constant to a sub 2 times t squared plus so on and so forth, plus some constant a sub n times t to the power of n. So adding two polynomials together in this polynomial space gives me another polynomial of the same form. So I stay inside of the space. So that first property is there. What if I want to talk about the 0 element? Well, in this case, the 0 element is really just the 0 polynomial. And I can have that 0 element in my polynomial space. It's going to be very boring. Now keep in mind, t is going to be our variable, and I don't want to say anything or impose any restrictions on t. T can be whatever it wants to be, right? We think of a polynomial, we're not thinking of a constant, we're not thinking of a specific value for the input of it. We're saying we're just a polynomial in general. What I do have control over, though, are the coefficients, the scalars, right? And I do have a 0 element in my polynomial space, which would namely be the 0 polynomial, 0 plus 0t plus 0t squared plus 0t cubed plus so on and so forth plus 0 times t to the n. And it is sort of underwhelming, but certainly if a sub 0, a sub 1, a sub 2, so on and so forth to a sub n are all 0, then that gives me the 0 polynomial, which is the 0 element in my polynomial space. And then we can talk about one more of these properties. Remember, there's 10 of them in total, but we're just going to focus on the 3 big ones for now, because I'm going to run out of space soon anyways. But what about being closed under scalar multiplication? Well, if I take a polynomial p at t, and let me just call this, a sub 0 plus a sub 1t plus a sub 2t squared plus so on and so forth plus a sub n times t to the n, so a polynomial of degree at most n. And I multiply this by some scalar c. We say, well, I can do that. I can multiply by a scalar c, and then I can think about distributing this through. And how is that going to look when I distribute c through? Well, I'm going to get c times a sub 0 plus c times a sub 1t plus c times a sub 2t squared plus so on and so forth plus c times a sub n t to the power of n. And all of these values, where I'm taking a real number, some a0, a1, so on and so forth, and multiplying it by another real number, is going to give me a real number. So I could go ahead and give this a new nickname. I could use sort of party hats for my notation. I could say, well, a sub 0 hat plus a sub 1 hat times t plus a sub 2 hat times t squared plus so on and so forth plus a sub n hat times t to the n, where these are all real numbers. These are still all real numbers. So I stay in that polynomial space. And you could show that those remaining 7 axioms hold true as well. But the idea really is that I can show that this is a vector space. So I can work with a polynomial space as well. What's very interesting about the polynomial space is that we could make the following claim. We could say that polynomial space Pn, P with this subscript n, is going to be isomorphic to traditional vector space Rn plus 1. we'll think, well, why is that? Well, when I already tell you a polynomial of degree at most n, you already have a very basic understanding as to how this looks. In fact, you know most about it. The only things that you don't know are what are the coefficients and what does the constant term look like. So if I really want to strip away the unnecessary information about a polynomial of degree at most n, then what I can do is I can just describe how those constants and coefficients look. So we could assign this polynomial to a vector. How would that vector look? Well, I need to know the constant term a sub 0. I need to know the coefficient on t, a sub 1. I need to know the coefficient on t squared, a sub 2, so on and so forth. And then I need to know the coefficient on t to the n, a sub n. So all I need to know are these constants and coefficients, right? I need to know, well, what are those? And if I know what those are, then I can build the polynomial myself, right? And you think, well, if I tell you I have some, quadratic, right, some polynomial of degree 2, what do I need to know? All I need to know is the constant and the coefficients. So let's say I have a function, right, a quadratic. Let's say I have something like 2 plus 3x plus 4x squared. I don't really need you to tell me the form of it if you're saying that it's a polynomial of degree 2. The only things that I need to know are what those constants and coefficients look like. So we're saying that we can actually just assemble the information into a vector, for example, 2, 3, 4, and I'll know the order it should go in. It should be 2 times x to the 0, my constant term, plus a 3 times x to the first, and a 4 times x squared. And that's kind of the idea. But we'll notice that in general, if I'm talking about a polynomial of degree at most n, there really needs to be n plus 1 terms here. Like, for example, if I have a polynomial of degree 2, I need 3 terms to designate, because I have this constant term to worry about as well, and the x to the first term and the x squared term. I need to know what those constants and coefficients look like. So we have a really nice way of thinking about a polynomial space in terms of a traditional vector space anyways. So you might think, well, this isn't really much different, and you're not really wrong. Let's work with these polynomial spaces a bit, talk a bit about them further. So I want to determine if the following set is a subspace of Pn, polynomial space with degree at most n, for an appropriate value of n. And I want to talk about all polynomials of the form p at t is equal to a plus t squared, where a is just some real number, a is in R. And so now, since I have a plus t squared, I notice the degree of this is at most 2. So I want to know, is this a subspace of polynomial space P2? Since I have degree at most 2. Now, in order for this to be a subspace of a polynomial space, I need those three axioms to hold true. I need those 3 pieces, right? I need to make sure I'm closed under addition, need to make sure I have the 0 element, I need to make sure that I'm closed under scalar multiplication. Now, in this example, depending on where I start with this, I don't think it's going to work out so nicely. So for example, if I work with addition first, let's say I take some example of a polynomial, let's say some number b plus t squared, and then another polynomial, call it q at t, we'll say some constant c plus t squared. If I add these together, I want to know, am I going to stay in the polynomial space? Am I going to stay in, well, really, am I going to stay in my alleged subspace, my proposed subspace? I don't know if it is one or not. We'll say, well, I add the constants b plus c, gives me some constant term. And then adding t squared and t squared gives me 2t squared. And this is a bit of a problem. We'll see why it's a problem. When I add a real number to another real number, it just gives me some other real number, so I could call this a plus 2t squared. But the issue is actually this coefficient on t squared. In order for me to stay in the description that I'm given, we're saying all polynomials of the form, the polynomial has to be a constant plus t squared. It has to look like that. It has to be a number plus t squared. I'm not allowed to have a number plus 2t squared. No one mentioned anything about a 2 in front of the t squared. That's not allowed. So this is an issue. So we'll say this is an issue. So this actually fails at this point. So this is in fact not a subspace of polynomial space P2. What's interesting is that you would notice that all three of the properties fail. If I take a polynomial like this and try to multiply by a scalar, so let's say c times p at t, which would be c times some polynomial of the form a plus t squared, it's really a similar argument. We'll say, well, distributing this in c times a, that's kind of fine. This is still a real number. But then c times t squared, I'm not allowed this unless c is 1. Any other value for c is going to serve as a counterexample. So this doesn't hold true for all scalars c. In fact, there's only one of these that will keep us in that same form, number plus t squared, because now I have this coefficient on t squared again. We'll say, well, so that's going to fail. Another thing to consider is if I'm looking for that zero element, I'm not going to have it. Right? My polynomials must be of the form p at t has to be some real number a plus my t squared term. Now, I have control over the real number, so we'll say, well, this could be any scalar, so why not let it be 0? But what I don't have control over is the t squared term. I don't have any coefficient on it. There's no real number in front of this, so there's no way for me to actually zero this out. So I'm not able to achieve the 0 element. So I'll say no 0 element. I would need control over the t squared term, which I'm not given any coefficient there. So the closest I can get is 0 plus t squared, but that's not going to give me the 0 polynomial. So this is not a subspace of polynomial space P2. And in fact, all three of those pieces that I have to check for a subspace fail. So no good. Well, okay, well, what about polynomials with degree at most 3 with integer coefficients? So how would this look? Well, we'd say, well, in general, a polynomial would have to be some value, let's say a sub 0 plus some constant a sub 1t plus some constant a sub 2t squared plus some constant a sub 3t cubed, where all of these a values must be integers. So we'll write up here a sub 0, a sub 1, a sub 2, a sub 3 must be integers. What if I were to take another example of this? So some other polynomial, instead of using a's, let me use b's, but same idea. B sub 0 plus b sub 1t plus b sub 2t squared plus b sub 3t cubed, where b sub 0, b sub 1, b sub 2, and b sub 3 must be integers. And what if I add these elements together? Well, okay, so if I add my constants together, I'm going to get a sub 0 plus b sub 0. If I add my t terms together and collect, I'm going to have a sub 1 plus b sub 1 times t. If I add my t squared terms together and collect my coefficient, a sub 2 plus b sub 2 times t squared. And if I add my t cubed terms together and collect my coefficient, it's going to be a sub 3 plus b sub 3 times t cubed. We'll say, okay, so then what's going on here? Well, if I add two integers together, that's going to give me another integer. If I take any two integers, add them together, it gives me another integer. I can say, well, this is c sub 0 plus c sub 1t plus c sub 2t squared plus c sub 3t cubed. And we'll notice that if these a values must be integers, and we also said these b values must be integers, then adding these two polynomials together generate another polynomial of degree at most 3, but that the c values are integers. So this works perfectly. What about the 0 element? What about our 0 polynomial? Do we have that? Well, how would that look? So the 0 element would be 0 plus 0t plus 0t squared plus 0t cubed. And remember, my constants and coefficients have to all be integers. We could say, well, good for us, 0 is an integer. So this works. I do have the 0 element in my polynomial space from the set that I'm describing. There's one more to check, that's scalar multiplication. Remember, all that we're talking about are polynomials that are degree at most 3 that have integer coefficients. And I want to know, is this going to be a subspace? I didn't write this down earlier, but probably got a good idea. Is this a subspace? I'll write it up here. Is this a subspace of polynomial space P3? Polynomials of degree at most 3? Question mark. Okay, I'm trying to find that out. We are closed under addition. If I take two polynomials of this type and add it together, I do get another polynomial that stays in that set. I do have the 0 element. What about scalar multiplication? Am I closed under scalar multiplication? Well, let's see. So if I take a scalar c and multiply it to some polynomial of degree at most 3 with integer coefficients, a sub 0 plus a sub 1t plus a sub 2t squared plus a sub 3t cubed, and distribute this through, I'm going to get c times a sub 0, c times a sub 1 times t, c times a sub 2 times t squared, c times a sub 3 times t cubed. Does this stay where I need it to stay? Does it still meet that description? And unfortunately, the answer is no. So this is where it actually fails. I was able to get 2 of the 3 properties, but this third property isn't going to work out. And you can think of some examples, because in fact, there are examples that will work for c, but it won't work for any real number. So for example, what if c is pi? If I multiply by pi, pi times an integer is not an integer. So that won't work. Or my favorite number, e won't work either. Right? If I take the real number e times an integer won't work. Right? That won't keep my integer coefficients. So this, we would say, unfortunately, this is not a subspace of polynomial space P3. Sad face. Oh, that's happy face. Make it a sad face. Depends on how you feel about subspaces, right? Let's take a look at another example. Thinking more about subspaces, thinking about spanning sets. Spanning sets are going to be very important for the course. And we'll talk a bit more about these in the next section as well. Let H be the set of all vectors of the form, and here I have negative 2t for the first entry, 5t for the second entry, and 3t for the third entry. And I want to find a vector v in vector space R3 such that H is equal to the span of that vector v. And I want to know, well, why does this show that H is a subspace of R3? Now this is not going to be a difficult process, and we're going to see lots of examples that sort of follow suit with this one. But if I take a vector of this form, where the first entry is negative 2t, next entry is 5t, the next entry is 3t, probably noticing that I can just factor the t out. We'll do that. Bring the t out, and I'm left with the vector negative 2, 5, 3. If I multiply the t back in, it brings me back to where I was. But this, we're saying that t can be any real number. And t is acting as a scalar weight, which means that right now I'm already describing the span of a vector. So what are we saying? We're saying this describes the span of the vector with entries negative 2, 5, 3. And this, of course, is going to give us a subspace of R3. Right? So we'll be able to follow up with this and say, so this is a subspace of R3. Our theorem guarantees this. We have a spanning set that we found. Let's go back and just sort of refresh what that theorem said. All the way back. It says, if I have vectors that belong to a vector space V, then the span of those vectors is a subspace of that vector space V. right? We talked about span early on in the course. Span is going to be very important for us talking about vector spaces and subspaces, because if I have vectors that live in a vector space, and then I consider the span of those vectors, that is going to give us a subspace of that vector space. And what are we saying in our example here? We're saying that this vector, -2, 5, 3, lives in vector space R3. It's got 3 entries in it. This vector lives in vector space R3. So then the span, we call this vector v, so then the span of this vector v is a subspace of vector space R3. And if you want to get very specific, you'd say that this is a one-dimensional subspace of R3. It generates a line in R3 through the 0 vector and this vector. So this is actually a one-dimensional subspace of R3, but is in fact a subspace of R3. It's all about finding that spanning set. So let's see this example. Let W be the set of all vectors of the form. We have 4 entries. First entry is 2s plus 4t. Next entry is 2s. Next entry is 2s minus 3t. Last entry is 5t. Show that W is a subspace of R4. Let's build a spanning set. So what I can do is I can take this description of my vectors, and here we'd make a comment. We'd say, s and t are real numbers. What I want to do is I want to split this into the sum of 2 vectors, one vector relying on s, one vector relying on t. So all of the s's over here, I have 2s, and then another 2s, and then, would you believe it, another 2s. And then for the 4th entry, no mention of s, so I'm going to write it in anyways as 0 times s. And over here on my next vector, I want all the t terms. Well, that's going to be 4t, and then I don't have any t mentioned, so that's got to be 0 times t, and then -3t, and then lastly 5t. What I can do, since s and t are just real numbers, think of them sort of like free variables. They're scalar weights, right? Bring s out as a scalar weight from the first vector, and bring t out as a scalar weight from the second vector. And this leaves from the first vector, I'm left with a vector of numerical entries only now, 2, 2, 2, 0. And in the second vector, leaves behind numerical entries 4, 0, -3, 5. We're saying, well, this describes the span of these 2 vectors. Right? S and t are just real numbers. These are scalar weights now, and whatever you'd like for them. So I'm describing the span of these 2 vectors. So I'll say this describes the span of vectors. What vectors do we have? We have 2, 2, 2, 0, and vector 4, 0, -3, 5. We're describing the span of these 2 vectors. And these vectors live in R4. They have 4 entries each, 1, 2, 3, 4, 1, 2, 3, 4. So let's say these vectors live in vector space R4. So the span gives me a subspace of R4. And truthfully, this is going to give us a 2-dimensional subspace of R4. You have to be careful with just generalizing that type of argument. I want to make sure the vectors are linearly independent, but we can probably tell by inspection that, well, okay, so these vectors are not multiples of each other. It's more difficult if we have more than just 2 vectors, but we'll be able to see that these are not dependent vectors. So in fact, what we really have here is a 2-dimensional subspace of vector space R4. So we do have a subspace of R4. We'll take a look at just a couple more. Here, let W be the set of all vectors of the form. We have a first entry 2a plus 3b, a second entry -1, and a third entry 2a minus 5b. where A, B, and C, and in fact, there's no mention of C here, so C for Corey, where A and B represent arbitrary real numbers. Find a set S of vectors that spans W, or give an example to show that W is not a vector space. Now, you might be looking at this and noticing something a bit different about it right away. And let's just go ahead and say what it is. That middle entry is going to create such an issue for us. Now, why would it create an issue? Well, right away, we could say in order for this to be a subspace of a vector space, and let's sort of talk about an idea that we want to sort of continue on with into some future sections. This is going to be a bit of a shortcut for us. Are you ready for a shortcut, for a pro tip from me to you? Let me know. Let me know in the comment section below if you're ready for me to give you this pro tip. And don't tell anyone that I told you, because I don't want to get in trouble. I want to stay on good terms with everybody. We'll say this. A subspace of a known vector space is itself a vector space. If you can show that something is a subspace of a known vector space, then that's going to serve as its own vector space as well. So in fact, you could go and you could show that the remaining axioms do hold true, which is going to be very fantastic, that I stay inside of that space. So subspace of a known vector space is also a vector space. But let's go ahead and take a look at what it is we have to say here. All right, I want to show either that I can find a spanning set or show that W is not a vector space. Okay, well, right away, there's some consideration to make. I think about that second entry. I think about maybe the zero vector first. Right, the zero vector is a good place to start here. How would the zero vector look? Well, these are vectors that live in R3. I have 3 entries. The zero vector of R3 would have to be 0, 0, 0. Will that work? The first entry is fine, right? A and B are real numbers, and if A and B are both 0, or if there's some balancing going on between them, I can get 0 out of that. What about for the third entry? Sure, that could be a possibility, but not at all for the second entry. The second entry must be a -1. So second entry must be -1. This is an issue. Sad face. I don't have the zero vector. So we'll say that there's no zero vector in our set. That's not the only issue, right? In fact, if I want to show that I'm closed under addition, I'm not. That's not the case, right? If I go ahead and take 2 vectors of this form, let's say I have a first vector that's 2a plus 3b. We do 2a0 plus 3b0 and then -1. And then what was it? It was 2a minus 5b. So we'll do 2a0 minus 5b0. And then I take another vector of this form. So just different scalars. Let me do 2a1 plus 3b1. And then -1 for the second entry has to be. And then the third entry be 2a1 minus 5b1. If I add these together, probably going to see what's going to happen with this. I can collect. So if I think about adding together, I'm going to have 2 times some real number, but that collected real number is a0 plus a1, and then plus 3 times the real number b0 plus b1. The second entry, this is the issue I'm going to have, -1 plus -1 gives me -2. And then for the third entry, it's going to be 2 times some real number. That's going to be 2 times a0 plus a1, and then -5 times a real number. That real number is going to be b0 plus b1. So it's that middle entry that gets messed up. So we'll say, well, what is this? I can't do that. I'm supposed to have this middle entry just be a -1. I'm not supposed to be a -2. What is the meaning of this? Can't do it. Bad. Not good. no good. So we'll say, well, this fails as well. So in fact, what we have here with our set, say this set W is not a vector space. I don't have the 0 element. I'm not closed under addition. Issues with scalar multiplication as well, right? If I multiply a scalar times -1, I can't guarantee that it's still going to be a -1, right? In fact, most likely not. Let's take a look at one more example, and then we'll head on out for the day. Let W be the set of all vectors of the form. We have first entry 2a minus b, second entry 3b minus c, third entry 3c minus a, and a fourth entry 3b, where a, b, and c represent arbitrary real numbers. And I'd like to find a set S of vectors that spans W, or give an example to show that W is not a vector space. We'll say, okay, well, let's see what's going on here. This actually looks like we could have some success with it. It doesn't look like I'm right away noticing anything suspicious about it. So what could I do? Well, I could try to split this up into 3 vectors. One vector relying on A, plus another vector relying on B, plus another vector relying on C. And I can try to build a spanning set. Now, relying on A, and I gotta be careful because things kind of jump around a bit, but I have 2A for the first entry, looks good. Nothing in the second entry, so 0A. Third entry, I have minus A, say minus 1 times A. And then nothing for the fourth entry, so 0A. What about B? So I have minus B, or that's -1B, 3B. Third entry is missing it, so 0B, and then 3B for the last entry. Then what about C? First entry is missing any mention of C, so that's 0C. Then I have minus C, or that's -1C. Then I have 3C, and then I'm missing C in the last entry, so that's got to be 0C. But then A, B, and C are just arbitrary real numbers. Think of them now as scalar weights and bring them out. So some vector times A plus some vector times B plus some vector times C. And this is going to leave behind vectors with numerical entries only. So this first vector, you guessed it, right? It's going to be 2, 0, -1, 0. Second vector is going to be -1, 3, 0, 3. Third vector is going to be 0, -1, 3, 0. But this is now showing that I have the span of these 3 vectors. Right? If I want to sort of nickname these vectors U, V, and W, what I have is I have the span of U, V, and W, where these vectors live in R4. So this is going to give me a subspace of R4. I have a subspace of R4. So the question said, find a set of vectors that spans W. So I can do that now. I can say the set of vectors that spans W is, I have a set. The set's going to have 3 vectors in it. That first vector is going to be 2, 0, -1, 0. Second vector, -1, 3, 0, 3. And the third vector is going to be 0, -1, 3, 0. And this is going to be my spanning set. Let's use that term right now, because we're going to be using it later on in the course as well. I have this spanning set. Hey, let me know what you think about all of this vector space and subspace stuff. Let me know what you think about polynomial spaces in general. Let me know how you're doing out there. It's great to be back. No matter where you are, make sure that you always keep learning, keep dreaming, and follow your heart. We're going to do more stuff with math and cats later on. You know, we'll be back at it before you know it. And hope you have a great rest of your day. And you know what? I will see you next time. Until then.